Hello everyone, it's Mr. Grant here. Today we are going to continue talking about thermochemistry. Last time we talked about Hess's law. Today we're going to look at bond energy in reactions as another means for predicting enthalpy change of any given reaction. At the molecular level, I like to think of chemical reactions like playing with Legos. We start with reactants that are made from certain Lego pieces or atoms, like these two molecules that consist of two hydrogen atoms and two chlorine atoms. Initially, the hydrogen atoms are bonded together and the chlorine atoms are bonded together. Chemical reactions are essentially just rearranging atoms. We never create or destroy atoms, we just rearrange them. So in this case, they can rearrange to form hydrogen chloride, two molecules of hydrogen chloride to be exact, because I can't have any Lego pieces left over sitting all by themselves in a balanced reaction. But unlike building Legos, reactions of atoms always come with an energy change. In this case, energy is released. But where does it come from? Well, hydrogen and chlorine molecules are reactive because they're relatively high in energy. When they react, they form lower energy molecules of HCl, and energy is released based on the difference in the energy between the reactants and the products. So when we say that a molecule is more stable in chemical terms, it means that it's lower in energy. And nature prefers things to be lowest energy states. Every day we eat foods containing high energy molecules like fats and carbohydrates, and we break them down into low energy molecules like water and CO2 so that our bodies can utilize that difference in energy. In fact, here's a European nutrition label, and you'll see that where we would have calories, it actually says energy. And the given units are kilojoules, which you should be familiar with. So what's actually happening to cause the energy to be released? Well, bonds are being broken and new bonds are being formed. In this reaction, a Cl-Cl bond and an HH bond are broken, while HCl bonds are being formed. But not all bonds are equal. Some are stronger than others. So to understand this better, we use the term bond energy, which refers to the amount of energy required to break a chemical bond measured in kilojoules per mole. Strong bonds require more energy to break, and stable molecules typically have strong bonds that are hard to break. So here's a table of bond energies that were measured experimentally. So if you want to, pause the video for a moment to see if you can find the three bonds from our reaction on this table: HH, Cl-Cl, and HCl single bonds. So here they are. Cl-Cl requires 242 kilojoules per mole to break. HH requires 436 kilojoules per mole to break, and then HCl single bond requires 431. In this reaction, we're dealing with 2 moles of HCl though, so we would double that number in our calculation. Note though that HCl bonds are not being broken in our reaction, they're actually being formed. So we actually will add a negative sign to that 431. Breaking bonds requires energy, but forming bonds releases energy. So let's add up the energy changes associated with this reaction to find the total enthalpy change, delta H. So I need to spend 242 kilojoules to break 1 mole of bonds in chlorine, 436 kilojoules to break the bonds in hydrogen. These are my bonds broken. Then I will recoup 431 kilojoules for each mole of HCl bonds broken. In this case, 2 moles are being broken. The total change here is 184, negative 184, which means that 184 kilojoules are released during this reaction. So here's a summary of what we just did, which I suggest that you write somewhere where you can reference it easily. The enthalpy change of a reaction can be predicted by summing up the energy required to break all of the bonds in the reactants, and then subtracting the energy that's released by the bonds that are formed in the products. This difference is the enthalpy change. A reaction that forms many strong bonds in the products will be exothermic, having a negative delta H. Conversely, a reaction that breaks many strong bonds in the reactants will likely be endothermic, having a positive delta H. If you have any questions, please let me know via email or on Google Classroom. Have a good one, everyone.